All right. Who would like to start us off with a prayer today? Thank you so much.
Dear Heavenly Father, we're grateful for this opportunity that we have to come and to learn calculus today. Please bless us with that prayer and learn that we'll be able to remember the things that we studied before, and we'll be able to understand the things that we're taught today. Father, we're grateful for this wonderful opportunity that we have to study here, and we ask that please help us to make it in the name of Jesus Christ.
Amen. First couple of announcements. I emailed out a couple of videos on the binomial theorem. We didn't have you watch those before, but please get on. I'm sure we will not cover enough in class over the next 2 or 3 days to satisfy your understanding for the binomial theorem. So please make sure you get on and watch those. Also, I canceled Project 7 so you can have more time to review for the final. Usually I have almost the whole week to review, the last week to review for the final, but it's not the way the schedule worked out this semester. So take the time to review. You might start reviewing very soon, for example, over Thanksgiving break. I sent out a link with the email when they informed me that I canceled Project 7. I sent out a link to the math department website where the old 113 final exams are. So there's like 10, and they have solutions. So I'd strongly encourage you to start going over them. I would try to go over all of 10 if you can. Then you'll feel really prepared. Well, let's cancel Project 8 too. I mean, so, yeah.
You can.
All right. So yeah, we're going to cancel both of those. So one of the projects I was going to have you do, the 2 projects I was going to have you do was to create a sign calculator using power series. We've done in the past, and also just do any problem of your choice that you could find using some math that we've worked with. So, but because we don't have much time to get to class this semester, why don't you guys work on take that time, make sure you do it. So, any questions? Sure.
So Maclaurin series is just a series.
Yep. That question was, is a Maclaurin series just a Taylor series centered at 0? Yes, that is correct. And it's not called Maclaurin, it's called Maclaurin. So you gotta say it that way, otherwise it's wrong. So, thanks, Brian. Other questions? Okay. The TAs do have a small flyer. There's a class. I'm in the math education department. I'm not a mathematician. My PhD is in math education. The research I do is in math education. We have an incredible math ed program here. If you've thought about maybe teaching math as a career, we have a Math Ed 101 class. It's a block class for first block next semester, well, every semester. And we have flyers that will be coming around for that. It's easy. You might think, hey, I've sat in who knows how many hundreds of hours of math classes. I think I have a pretty good idea of what it takes to be a math teacher. But you've also read how many hours of novels, and you probably don't think the same thing about that you could be a good author of a book. Or you've driven how many hours in a car, and you don't think that you could design a car, right? There is a lot more stuff that happens in being a math teacher than than what you see in class. And this will start to introduce you to some of those things, some of the things you have to be thinking about as you are a math teacher. And the colleagues that I have teaching that are really, really English. So they're much better math teachers. So I know those analogies aren't perfect, right? But still, there is a lot more to teaching than you understand as a student. So before we dive into doing problems today, I just want to do talk about a few things of where power series and Taylor series are used, and series in general. It's not much of a stretch to say that actually series kind of rules your technical life. So we'll talk about some of those. So we already talked about a lot of the computational stuff that series do, but that's not the only place that series are used or Taylor polynomials are used, although it is used a lot there. But right now you haven't seen it because it's very much in the background. Another place that they're used is to simplify formulas or simplify equations so that you can get solutions or approximate solutions. For example, in economics, how many of you are econ majors here? What? Only one? Good. Well, I'm impressed. Nice job. I love economics. So you often have formulas in economics where it comes up with the natural log of 1 plus r, where r is an interest rate or a growth rate. And in your reading, you read about a series 1 plus x, it equals x minus x squared over 2 plus x cubed over 3 minus x to the fourth over 4, etc. Well, interest rates are usually pretty close to 0, right? 3, 4, 5. Some growth rates will get 10, 12%. But since they're close to 0, you can actually simplify this crazy thing with just r. Because if you're close to 0, these are all going to be really small, right? If you have like 2%, you square 2%, you're going to have like 0.0004. I divide that in half. Like, these things are going to be really small. So you actually get a good enough approximation just by looking at taking r as your estimate instead of the natural log of 1 plus r. So in physics, if you study pendulums, figure out the mathematics of pendulums, you end up with this equation. It's a differential equation. This is to get a function that tells you like the length of the swing depending on the theta, the angle that it swings. You get this equation, that the second derivative of the angle with respect to the time is equal to g, which is the gravitational constant, over L, which is the length of the rope, times sine of theta. Well, this is impossible to solve. Okay? In differential equations, you cannot solve this equation. Okay? But if you're not swinging things very much, if your angle is going to be pretty small and you're just going to be swinging it like this, that theta is pretty close to 0. And if that's the case, then why not replace sine of theta with just 0? Because sine of theta is about, here, let me do it into sine of x, you guys are more comfortable with that, is about x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, right? But when x is small, these things don't make much of a difference, so just replace it with x. So that's what they do. They replace this with x, and then you can solve things, and you get solutions that you may have seen before if you've studied much physics.
That's right. So I don't know about most, but a lot. So a lot of the formulas you've learned are actually they're first order approximations is basically what you've done. You've taken a Taylor polynomial that's just a linear approximation or a quadratic approximation and used that to derive formulas to use. Yes? So that's a great question. Yep. So this is the Wikipedia page for the mathematics of a pendulum. You scroll on down, and you end up with, see all of these series down here? You can't cut it off at just x. So you have to start building these series. There's actually two series going on here. One, to approximate the function, they actually build a function that they can't get explicitly with just term by term of a power series. That's this one right here. And then, but that has sine squared of theta in it, a sine squared of theta over 2. And to get rid of that, they actually replace that with a power series, and they multiply all those terms out and start combining terms. Like at the end of 1110, it talked to you about how to multiply two power series, and you do it term by term and combine the like terms. That's what they do, and they end up with, let me move that at the very top. They end up with that crazy thing. So if theta is small, all of your thetas there are going to be close to 0. You can get rid of that, and you end up with just your 1, and you end up with the equation that I had before. But there you can take it out for as far as you need to get accurate approximations. Nice. You asked the perfect question. So, Boyles' law also in chemistry. Oh, can I take as one cool fact about a double pendulum? Do you guys know what a double pendulum is? It is a pendulum on a pendulum. So you have two things that are swinging. So you have one pendulum swinging, but it's attached to the center of the pendulum above it and is swinging. These are very chaotic. They're practically impossible to model. And if you have a well-oiled double pendulum, it is so sensitive to initial conditions that the gravitational force of a raindrop a mile away will affect its position within 60 swings. Yeah, the gravitational effect of a raindrop. I mean, it's like nothing, but it is so chaotic that you just change it. That much of a difference in the environment will change the position that it's in within 60 swings back and forth. Yes. Oh, I'm sure you can get them just on Amazon. Yeah, they're around. So crazy, just crazy. All right, Boyles' law. So a lot of you, you chemistry majors, you guys know chemistry, or if you've had chemistry, you've learned Boyles' law. Okay, this actually is not. People are pulling up videos of double pendulums. Right, is that what you're doing? So, Boyles' law is actually just a first-order approximation. It's pretty good as long as your pressure isn't too high, but when your pressure gets high, you actually have to use different things. Some of you probably just recently took a test on this. So you actually you put in a series. Where did my series go here? Pressure is equal to RT over V times 1 I think that's V squared. I can't remember if it's V or V squared. But it's a V, but a different coefficient? I can't remember. It must be V squared. So then when the pressure is high, it's not a very good approximation. You have to start solving for these coefficients. And to solve for that coefficient, you actually have to do an improper integral, which is something else we covered in class, which is kind of crazy. Yeah. But I won't take the time to write it up. Okay. So yeah, a lot of the formulas you've learned are actually just first order approximations, or they're hiding in solution somewhere. Probably the place where series impacts your life the most is not a power series. It's actually Fourier series. So Fourier series, a power series takes lines like this, and then y equals x, and then y equals x squared, and y equals x cubed, and it adds up combinations of those to get different curves. Right? That's what we were doing, a constant x, x squared, x cubed. But Fourier series takes sine curves. It turns out that you can make any curve you want. You can even draw any curve you want with just sines. Powers of different, not powers of sines, but sines of the things like sine of x, sine of 2x, sine of 3x, and adding up combinations of these. So you have this sine wave. Oops, that's not a very good sine wave. Double the frequency, triple the frequency, quadruple the frequency, and you add up different values of those, weighted values of those. And why do you guys care about that? It's because every single piece of music that you listen to has been encoded using Fourier series to make it so it easily streams or easily compacts to a very little size. Like MP3, that's basically what they do. They take the actual data that they've collected with the actual audio, and they just take sinusoidal approximations out far enough so you can't tell the difference. And then I think they just send coefficients of those terms to your new computer, and it just generates those for you instead of all of those things. I'll put up a video you guys might enjoy about how Fourier series can be used to draw any picture also. So it's kind of crazy. All right. So what's the point of 1011? Well, 1110. Let's do a quick recap. So we started off by finding approximations to curves. We did a linear approximation, and then we extended those to quadratic and then cubic. And we did that by writing down things like ax to the cubed plus bx squared plus cx plus d. And we found good approximations by trying to match derivatives to polynomials. And then you do that enough, you see a pattern. Then you can just write down. This is what Taylor was known for, writing down the formula, so you don't have to write down things like this every time. If you find the derivatives, you can divide by the n factorial, multiply by x minus a to the nth power, and that gives you your series or your polynomial for however far out you want, approximating curves that way. Well, part of 1110 is finding ways so you don't have to take derivatives every time. We're going to do that for some basic things. We have already for e to the x, sine of x, cosine of x. But then let's use those so that we don't have to take derivatives all of the time. You'll still do some work taking derivatives, but we're going to. You don't have to take derivatives. For example, one of the problems I gave you was to find the power series for this on Monday, right? You took derivatives. Well, if you think of the power series of e to the x, if you just think of the power series of e to the x times x, then you can just distribute that x to every one of your terms. 1 plus x plus x squared over 2, x cubed over 3 factorial, ... So you distribute those out. You get x plus x squared plus x cubed over 2 plus x to the 4th over 3 factorial, etc. That's pretty easy, right? Not too bad. Much easier taking derivatives. And some of you noticed this pattern on Monday. So we can do things. We can take known series and we can multiply by x. We can substitute in things. And we can take antiderivatives or we can take derivatives to get power series of new functions. So everyone quickly find the power series for sine of 2x. If you know the power series of the sine of x is 1, oops, not 1. There's my work. So I know the power series for the sine of something. So, and I think about this as the sine, if I think about it as the sine of something, and then I have these powers of something divided by those factorials. So everywhere there's that something, I replace that something with 2x. So well, the 2x goes where the x is on each of those terms. And so I get, instead of x, I get 2x. Instead of 2x x cubed, I get 2x cubed. Instead of x to the fifth, I get 2x to the fifth. I plug it in, then I simplified, and this was what I got. Oops, we better put some indices on there. So this is from n equals 1 to infinity. Sorry, what was that? It depends. It depends on where you start your indice. So if you start at n equals 0, then it's 2n plus 1. If you start at n equals 1, then it's 2n minus 1. So, yeah. It's one thing that can be confusing about these is because you can write the series in ways that look different, but they're actually the same. So, thanks for bringing that up. Is that your question? Okay. All right. Any questions on this? You mean like where it starts?
Yeah, so like the n plus 1 and n minus 1, is that your whole series, or is that just the cosine sine?
You mean like where you start at 0 or where you start at 1?
Yeah, I think it's minus 1.
Yeah. So you could actually start writing down your series and have it start at any value. I could rewrite the e to the x one. Have I written down the e to the x one yet? Well, I did right here. I could rewrite this thing and have it start at like n equals a minus 2 if I wanted to. But then that would be x to the n. If I want my first power to be 0, for my first term when I plug in a minus 2, if I want it to be 0, then I would have to add 2. And down here I would have to have n plus 2 factorial. Like these are exactly the same. You've just shifted your index, but every single term will be exactly the same as the other ones. So, yeah. But yeah, if you start changing the index, then you start adding or subtracting things. Okay. Other questions? Okay. Let me turn you guys loose on these. So I want you guys to find a power series centered at x equals 0 for these 4 things. And I'll write down a hint here for this one. Yes. So, yeah, so it gave you a table of known things, and I'll write down like the 3 that we'll use here. So I'll write those down up here, but I won't have I won't be able to keep them up the whole time when we start writing them down, but yes. So things you should know, that e to the x to the n over n factorial, 1 over 1 minus x is the geometric series. Oops. And the natural log of 1 plus x is there you go. Yeah.
Yes, you absolutely do. So, by the time we're done with by the time we're done with all the sections, you will have used most of these so much that you'll have them memorized. But yeah, all of the ones in chat in that one table in this section are really nice. I guess you don't have to. I mean, you can start taking derivatives and figure out what they are. You know, but it's a lot easier to have them memorized. It's a good question.
Okay, let's start going over these. It's nice in my small class. I just pick students out and they write them up on the board, and so I don't have to be writing out the solutions, and they can be getting up on the board while I'm walking around. Maybe I should have you guys come up and just start writing on my tablet. But okay. And of course, when I'm writing on the tablet, I often hide the problems that you're supposed to be working on. It's one of the disadvantages this way. All right, so the first one, e to the negative x squared. Well, let's use what we know. Instead of just starting to take derivatives, we do know what e to the negative x is, that power series centered at 0 for e to the negative x, for e to the x. And so here, the difference is we have a minus x squared where we had an x. So everywhere there's an x over here in the series, we're going to replace it with a minus x squared. So instead of x here, I'm going to have a minus x squared. So I substitute that in, and now I have x to the 2n minus 1 to the n over n factorial. That's just after doing the algebra to simplify. Questions on that first one? Yes? So the question is, find the power series centered at x equals 0 for this expression. Okay. So we do have another technique. We could start taking derivatives and use the Taylor series formula. Use this thing, but it's a lot easier to use. We've already done that for e to the x. We don't have to do it some more. We can just use substitution. Okay. All right, here's this number 2. I can rewrite this as x squared times something I already know the series for. So this is the geometric series. As long as x is between a minus 1 and 1, then we can evaluate what that with this. So I replace that with its series, and then I just multiply in the x squared, and all it's going to do is raise my power by 2. So x to the n. So when I was in your shoes, I liked to write out the series and do every step with the terms. It just helped me keep track of things better instead of just doing everything in terms of this summation notation. I wasn't super comfortable with the summation notation. You guys might not be either. So I would write out something like this, and then I would distribute that out, and I would get x squared plus x cubed plus x to the 4th plus x to the 5th, dot, dot, dot. And that would be my new series, and then I could figure out what the general term was. So then I'd know that's, if I start at n equals 0 again, I would have n equals 0 to infinity of x, x to the n plus 2. So this is one, I could actually make it look like x to the n. I would just start at n equals 2. So these are the same, but I just dropped my first terms because my first 2 terms end up disappearing when I multiply. They don't end up disappearing, but they end up not being in this new set here. So I could rewrite it just by changing the indices. Right? Yeah. So you might have to work backwards. We don't give you crazy ones, but yeah. Okay. Side note on this. I once had a guy in my ward when I was a student here, and he said he was a philosophy major, and one of his philosophy teachers told him that you could add up enough positive numbers and get a number so big that it would equal a negative number. and his proof was he took this series. He took the series 1 over 1 minus x, 1 plus x squared plus x cubed plus x to the fourth, right? This is the geometric series. And he said, look, if you plug in 2, x equals 2, then on the right side you get 1 plus 2 squared plus 2 cubed plus 2 to the fourth, right? You're going to add that up. You're adding up a whole bunch of larger and larger and larger values. But if you plug it into the other side, you get 1 over 1 minus 2, and that just equals a minus 1. So we added up so many positive numbers that we ended up with a negative number. So what did the philosophy professor not understand? He didn't understand that this is only true when x is between a minus 1 and 1. So it's not true for every single x. So this only converges for values that are between a minus 1 and 1. You can't plug in just any x and have the left side equal the right side. So anyway, side note. Okay. So arctangent. All right, so here we're going to find, let's find the series for 1 over 1 plus x squared first. And to do that, we're going to use this series, the geometric series, the one we just had, x to the n. But to connect these, we need to rewrite this as 1 over 1 minus something. And then whatever that something is, I can plug it in wherever there's an x over here. So how would I rewrite that as 1 over 1 minus something? What's that something? A negative x squared. So now I can rewrite 1 over 1 plus x squared as a minus x squared to the nth power. That sum, let's simplify that. Okay. But that is not the series I care about. I'm trying to use this to get to arctangent of x. So how can I do that? Well, if I find the antiderivative of this, then that will equal inverse tangent of x, or get me at least within a constant of arctangent of x. So what's the antiderivative of these? So this again is a place where I like to write it out term for term. So that would be at n equals 0, I got 1 at minus x squared plus x cubed, plus x to the fourth minus x to the sixth, etc. And the antiderivative of that would be x minus x cubed over 3 plus x to the fifth over 5 minus x to the seventh over 7, etc. Plus a constant. So we have to remember that constant to make sure we get these, to get it right. So I could rewrite that as, well, let's solve for the constant first. What value could I plug into both sides that would make it easy to solve for that constant? Sorry, what? 0. Because at x equals 0, x equals 0 to solve for someone go close those doors. Where's Brinley? Yeah. Great, yeah. Chelsea, can you go close this? Thanks. to solve for C. And then you get inverse tangent of 0, which equals 0, also has to equal C, because all of these terms will go to 0. So C equals 0. Great. So we don't have to worry about that C anymore. And I could rewrite the inverse tangent of x as the summation of x to the 2n. Where do we start at? N equals 0. X to the 2n plus 1 over 2n plus 1 with a minus 1 the n. Yeah. N equals 0 to infinity. So now we have that. There's our series. Now what happens, in this case, what happens if we plug in 1 to both sides? We get a series over here. The numerator is going to be 1, an alternating 1, and you just end up with 1 minus a third plus a fifth minus a seventh plus a ninth. But what's the inverse tangent of 1? Pi fourths. So we just created a series. If this converges, does this converge? We better make sure. Is this a convergent series over here? How do we know? Alternating series test. Terms are going to 0, and each one is smaller in absolute value than the one before it. So it converges, and it converges to pi fourths. So we just created a series that we can use to approximate pi. We can add up this side, the right side, and then multiply by 4. You'll get an approximation of pi. The only problem with this is it takes you have to add up a whole bunch of terms. It converges very, very slowly. So you have to add up a whole bunch of terms to get a good estimate. All right, have a great day.